Get back. I'm all right, Jack. Keep your hands off of my stack. Mommy, it's a hit. Don't get me back to good bullshit. I'm in the high fidelity first class traveling section. I think I need a lift jet.
Good morning, everyone. Thank you very much for attending our advanced controls webinar for mining applications. My name is 𝗦𝗧𝗦𝗦𝗬𝗓. Thank you very much for joining us. I got my good friend here, Devin Marshman. Devin, how are you today? You're muted. There
Of course
you
I am. Morning, Sylvain. Yeah.
Awesome.
Thanks for having me. I'm doing well.
Awesome. So I am the process optimization specialist for Lakeside Process Controls. Devin, you are a solutions architect for Spark Control. What does a solutions architect do?
Good question. Yeah, it's a pretty generic title.
It is.
But I've been working in the field of advanced process control with Spartan for the last 15 years. So in my role as solutions architect, I get to work with end users on developing new solutions or enhancing solutions that fit their applications at their specific site. So it's a fun job.
Awesome. Yeah. No, I know exactly. As for myself, yeah, I do. I do webinars. I've been with Lakeside since 2011, whatever. That's what, 13 years, and been in the field for 30 plus years. I've seen a lot. I teach courses and so forth. So maybe why don't we just begin here? And some guidelines for people out there. Once again, thank you for attending. Your microphones are off, so therefore we cannot hear you. Um, there will be a Q&A session at the end. Feel free to type in your questions anytime you want through the Q&A dialog box as I show there. So we will be answering your questions, probably more specifically. Devin will be answering your question. He's the smart one here today. And there is a 10-second time delay from the moment I speak to the moment you hear me. And that's just for better buffering and quality of presentation. So if you think that if light travels at 300,000 kilometers an hour, that means Devin and I are actually located in our spaceship here. I didn't manage to refuel it with element 115. So we're near the Lagrange point. And so that's why there's a 10-second time delay. We can see the James Webb Space Telescope just on the horizon. So I believe, yeah, we can see your questions. Can't remember if everybody else can see them or not. There's no such thing as a bad question, so I encourage you to ask questions and so forth. If we do not have time, or you think of a question later on, or we do not answer your question satisfactorily, you can always feel free to reach out to me. That's all my information is located in those little black and white squares there. You can reach out to me and we will make sure that we answer your questions adequately. If you go to the handout section, if you do any kind of flotation controls web search, Devin's name comes up all the time. So there is a paper that he has published in conjunction with Ian. You can download that through the handout section. So you just click on handout and you can download that. It is yours to have. This is part of a series of webinars that I've put together. So I do have up to 14 webinars out there. They are recorded. Should you wish to have if you wish to view them, if you're really bored, then you can actually go and send me a message. I will actually then send you the links to that. There's also a podcast actually that is out there. It's on YouTube. as well. Don't know if I actually have it there. No, I don't have it there. There's a podcast as well that you can download it. It's on YouTube. It's called the generic name is called Closing the Loop. Make sure Closing the Loop Lakeside. If you go on YouTube, you can find it. There's a series of, I think the podcast that I'm on is number 6, I believe, but there's a few other probably more interesting people than myself. A bit more. A week today, we will be hosting at our facility in Mississauga the Lakeside User Exchange, and you can scan that QR code to sign up for it. I'm just looking here. Feature user case studies, maintenance and reliability best practices, technology updates. You'll obviously expert panel and social and networking opportunities and technology exhibit. But the most important thing about this is that we feed you very, very well. So I encourage you, if you want some good food, to drop by. It's free to attend. So. This is actually recorded as well. So if you do have to skip out early, or you want to share this with somebody else, or you're, again, if you're really, really bored, you can actually go back and watch this again. And I'm the boring part, but the Devin is actually the very, very, the more interesting person there. A bit of a safety moment. Yes, I know, a kind of nerdy humor there. It is summertime. Obviously, barbecues, parties, and everything else, and so forth and so forth. Be careful. Obviously, don't don't drink and drive. Don't drink and drive. Otherwise, you may be integrated with the police, and so therefore you do not want to do that. So be very careful. Be mindful. I know. I mean, I enjoy my beer, and obviously, but never do I partake and drive afterwards. So just be aware of that. A little bit about Lakeside. We'll get into spark controls and relationship in a minute here. Lakeside, this is a bit of a dated slide, actually. We are over 400 employees. We have offices in, obviously, Mississauga, Sarnia, Port Elgin. We have a newer facility, it's not that new anymore, in Dundas, Ontario, where we actually do a lot of our fabrication. So we do skid manufacturing there. Uh, Traditionally, Emerson used to do the valve repair services. That has been since downloaded to the Emerson Impact Partners. We'll talk about that. And so we do a lot of our valve repair business there. We have offices in Sudbury, Thunder Bay, and Winnipeg as well. And like as I mentioned, we are part of the Emerson Impact Partner. Again, I think this slide is a bit dated. I show 21 Emerson Impact Partners throughout North America. I believe it has actually gone down to 18 or 19. I'm not sure. So Lakeside's territory starts just from this side of the Kingston. I was in beginning of May. I was in Napanee, Ontario, Eastern Ontario. That is our territory, begins there, all the way to the Manitoba, Saskatchewan border and parts of Nunavut. Spartan Controls is to the west of us, and it's from the Saskatchewan, BC, most of North Territories, and parts of Nunavut as well. Uh, what are we going to cover? We're going to talk a little bit about the relationship between Lakeside and Spartan. We're going to talk about advanced control. What is advanced controls? And then we'll get into more specifics application that Spartan offers with Spartan Pro Solutions. We're going to show you sort of and Devin Kuringer, I call the bread and butter, probably the more common applications that are out there right now. But there's a part of a family, of a suite of a lot larger offerings and solutions that Spartan offers. And then we'll talk about more of the implementation, the practical side. How do you implement this? What kind of timeline? And how do you the magic word of 2014, 2024, 2024 is sustainability. How do you sustain that technology and get the maximum out of your technology. So the relationship, obviously, as you can see, Lakeside and Spartan, we are both Emerson Impact partners. It's been a long-standing relationship for as long as I can remember. Emerson decided that instead of having a large monolithic presence throughout the market, they decided that it was better, the customer was better served having a local presence. And I believe it's actually worked very well. And so Spartan has obviously their customers. Lakeside, we have our customers. We also work together as well. So there are certain things that Spartan offers that we leverage off, and likewise, Spartan will leverage some of the stuff that Lakeside offers. So it's very complementary. And so, like I said, since Spartan actually offers these Spartan Pro solutions, it's we leverage off of that, we learn off each other, and then we're able to support each other as well. Uh, as I said, these Spartan Pro solutions cover many different industries. Obviously, we're going to be covering the mining industry, but those of you oil and gas, oil sands, I spent a fair bit of time myself in the oil sands way back when. The coldest temperature I've ever seen was minus 48. It was January 4th, 2010, minus 48 degrees. Devin, what was the coldest of your experience?
I don't think I've hit minus 50.
Okay.
So it's probably right around there
Right
too.
around there as well. Yeah,
Yep.
exactly. But it's a dry cold, so it's like a dry
It's a
heat.
dry. Yeah, that's right.
So it's yeah, it was cold. And obviously refineries, pulp and paper, lime kiln applications and so forth. We are actually in process of collaboration with Spartan right now in some of these applications in different industries right now. Um, let's talk about more specific this Spartan Pro solutions for the mining application. There's the hard rock application, Spark Pro, SAG. So SAG, for those of you who don't know, SAG stands for semi-autogenous. I got it right. Autogenous, right?
Nailed it. Yep,
Awesome.
you got
Not
it.
autonomous, autogenous grinding and the ball mill as well. We'll get into specific of what those actually processes mean. Then we got soft rock applications as well. Then you got the more common types of processes, floatation, thickener, and a whole slew of family of applications as well out there as well. In this webinar, we're going to deal with the SAG, the grinding part, the flotation part, as well as the thickener parts. Uh, so Spartan's not new at this. They actually have been working at this for quite a while. How long has this Spartan Pro solution been in on the market? Let's say, Devin.
Yeah, so Spartan has been doing advanced control. I haven't been doing it, but Spartan's been doing it for over 20 years now. The first advanced control application went up in 2001. So since then, we've grown our advanced process control team and capabilities, expanded in new industry, and we really got into the mining industry a little bit over 10 years ago.
Okay.
And I've been doing it since then.
Right. Now, how many advanced control engineers does Spartan employ?
So our team now is up to 18 advanced process control
18.
engineers full
Wow.
time. So yeah, largest group of advanced process control engineers in Canada, and I believe the largest one north of Houston.
No kidding. Obviously, those of you know Houston, the impact partner is Puffer Controls, and it's always a bit of a fight between Spartan and Puffer as to who's the largest one all the time. So, and for the obvious reasons, obviously of the abundance of oil in both regions there. So back to this slide right here. So obviously you got a lot of mining experience, and you can see here the estimated annual benefits is I see 500,000, a million. I mean, this is the kind of benefits you can expect from advanced controls in your mining applications. And it's not just obviously, and it comes also, you talk about runnability, be able to run more consistently. Those are some of the intangibles sometimes. Throughput quality, you'll see that also. And obviously minimizing energy consumption. I don't know, Devin, do you have anything else to add to that?
Yeah, I'll just say, results are going to vary depending on where your baseline is and where your starting point is. And, we have worked with sites where they've been significantly bottlenecked by their things like their grinding circuit. And the benefits from that can be upwards of nearly $50 million a year. So they can be far, far north of this.
No kidding, no kidding. As a matter of fact, one of the applications, just let you know, that we're working on here with Spartan Controls, one of the estimated. This is not in the mining application, but the estimated benefits that we're looking at is in excess of $2 million a year. So that is what advanced controls can do when properly applied. And what's the word again? Sustained.
Yeah, that's a big part of it for sure.
Exactly that. So why do we want to do this? So I got some charts here, some prices for different minerals, and these are a bit dated, and these bit gold prices over the last little bit. Gold has been traditionally, I just looked at it this morning. It's been steady on the rise actually. So gold is usually a very very safe bet. We got nickel. Actually, I just look at nickel kind of rebounding a little bit here. But the prices did drop for a past year, but I think they're rebounding a little bit. Copper as well has been rebounding a little bit here. Palladium is that's a bit of a different story. During the pandemic, for a while, palladium was actually more expensive than gold, believe it or not. But it's come back down to more reality, if I'm not mistaken. And why am I showing you these kind of, not, I don't want to say depressing slides, but mineral prices, let's face it, we know are volatile, and prices come on sometimes depending on anything from demands to geopolitical events and things like that. They're volatile, and so it's kind of hard sometimes to economically plan if you're a mill manager for your mine, if you're a CEO. And again, what we're trying to do here is, so we're trying to give you the best of both worlds, to increase throughput when times are good, maximize efficiency when prices are not so good. And so you're trying to get the best of both worlds with advanced controls. And in Ontario, Manitoba, I was surprised to see this actually. So there's over 16 active gold mines in Ontario right now. There's one in Manitoba. And you can see here copper, zinc, silver, uh, palladium, palladium, platinum, and so forth. There's even lithium mines actually are coming into play. And you can see the advanced exploration there. There's also significant numbers. So there's a tremendous amount of opportunities within Ontario and Manitoba right now, and to be able to actually implement some of these applications. Now, why? Obviously, I kind of touched about this. Why do we want to do this? Well, yes, we talked about increasing throughput. Prices are good. Hey, let's get the tons out the door, the ounces, or whatever we need to do. Increase yield, maximize. Let's face it, some of these, especially some of these gold mines, are not always the richest. Some of them that we deal with, I know, have 1 gram per ton, 2 grams per ton, which is kind of lean. Some of them go up to 9, 10 grams, and maybe up to 20 grams. But let's say 1 to 2 grams a ton. You got to be very efficient to be profitable. You got to process a lot of rock to be able to get some gold out. Energy costs, obviously, we know that energy cost is always a concern. Reduced carbon footprint. We actually, and it's obviously proven technology, and we all know about our beloved carbon tax. I'm not going to get on my soapbox or anything like that, but greenhouse gas emissions and so forth, we know that that is a concern to the industry, to us all, actually. Now, one thing I see there also, government incentives. There are numerous government incentives. Maybe Devin, can you attest to that a little bit here, or add to that government incentive programs that are out there?
Yeah, definitely. There's lots of avenues for government incentives, especially when it comes to energy saving projects. Lots of those are offered provincially, but there are also federal programs through NRCan
Okay.
that are available. So please
What
reach out
kind?
if you
What
want more
kind of?
information on those.
Yeah, exactly. We can actually, if you're interested, we can help you out with some of those links as well. What kind of subsidies do we look at typically?
Yeah, so they'll do subsidies for typically for studies to uncover, what the potential benefits of doing a project or implementing a new application to save energy would be. And they'll typically fund between 50 and 75% of study costs.
No kidding.
And then they'll do the same for projects.
Okay.
Now, obviously, if you get there's an upper limit on the total size of the project. So if you're looking at, replacing a boiler or something like that, that's a bit of a different story. But for something like advanced process control in that sort of price range, there's lots of funding programs available, again, in the range of 50 to 75%.
No kidding. That's awesome. No, it's good to know. It's and like I said, we can help you out if you're we can help you out with that. Reach out to me, and then we'll be able to set you up with some of the proper links of what the proper avenues. It's a bit of a labyrinth, if I'm mistaken. I know NRCan. I think you sent me a link once. It's almost like a one-stop shopping, at least website there as well.
Yeah, and they try to organize all the provincial incentives, which definitely vary by region.
Perfect. Because I know it can be a bit of a labyrinth as well, so it's not always evident. So, all right. So, what is advanced control? Well, before we talk about advanced control, we got to talk about what simple control is, and I think we're all aware of our regular controls that we have out there: single input, single output. You have a flow controller. That in this example here, the output will talk to a control valve, a positioner, a control valve, and so forth. The process will react, and then we measure the change in that process using some sort of measurement technology, and then it comes back. And this is known as a single input, single output strategy. But let's face it, we know that no loop is an island unto itself, and we know that processes can be highly interactive. And this is where advanced controls comes into play. Now here I'm showing you here, this is in our 𝗪𝗕𝗦𝗓 system. It's called MPC, Model Predictive Control. It comes in various flavors. I'm showing here MPC Pro. There's also MPC Plus. There's probably pros and cons, and we're not going to get into the specifics of which block to use. But the idea here is that this block can actually bring in multiple inputs. And I can't, Devin, do you know how many inputs it can handle off the top of your head typically?
Yeah, up to 80.
80. So
Yeah,
you could
lots.
probably fly an Airbus with this probably. So, or a SpaceX rocket, who knows? So inside that algorithm, there's obviously there's a specific algorithm. It will then talk to multiple outputs as well. These obviously will affect your process, and all those measurements come back. So this is called a multiple input, multiple output algorithm as well. Now, in the old day, well, not the old, in it's simple, single input, single output, we would call the measurements, we call them PV, process variables. The nomenclature kind of changes when you get into advanced controls. The measurements are called control variables. The outputs are called manipulated variables. One last thing as well with this MPC algorithm is that it takes into account the interactions, meaning that if I make a change on my output one, it's going to affect my other control variable. Therefore, I'm going to do the equal and opposite change on that to minimize the interactions. And it takes into account all the interaction between all the inputs and be able to minimize interactions on these as it makes a control action. It also takes into account disturbances. So you got this other measure. You think of it as feed forward. Basically, that's exactly what it is. So you got this other variable out there, and every time it changes, it affects one or two or three of my control variables. And so therefore, it can actually take into account and do some sort of feed forward control to compensate for these load variables out there. It also deals with constraints. So you want to be able to maximize one or two variables. The algorithm, when programmed like this, will actually drive the output to a certain maximum constraint that we set it to drive the whole, maximize the whole throughput. And one last thing as well is for a simple PID controller, it does not like process dead time or time delay. A PID controller is a very, very impatient beast. It makes a change. It wants to see a reaction right away. MPC is able there to compensate for the time delays. We tell it how much time delay there is, and therefore it builds quote unquote patience into the controls and be able to compensate for it. It's a dead time compensator. So it's very, very sophisticated, very advanced controls actually. So how do we do this? Well, you could do it two ways. If you have a Delta V system, the MPC Pro, the MPC Plus is native to the Delta V system. So it's actually incorporated within the actual control system, makes it very transparent, very open. But you can say, well, what if I don't have a Delta V system? You can still implement it. And what we do is that we implement the inside, let's say, a PK controller. Devin, is there other ways we can implement it and on the non-Delta V? We show a PK controller. Can we implement it in different ways as well?
Yeah, we can also do a server-based solution there as well. But the PK is becoming easier and easier and a more
Got it.
popular choice for sure.
Okay, and then obviously this PK controller would control with your current control systems, your DCS or your PLC via OPC-UA, whatever OPC-UA means. I don't know. The funny thing about OPC actually, if people don't know, we talk about OPC all the time, but it's an acronym of acronyms, which is kind of funny because O is actually OLE, Object Linking Embedded Process for Process Control. But I digress. So Devin, just give us an example here. You've done DCSs. Can you give us a bit of range of other makes of DCSs you've implemented this? Not necessarily in the mining industry, but overall in your advanced controls applications.
Yeah, no, you name it, and we've layered on Delta V for advanced process control on top of it. So
Okay. All
Honeywell,
right.
ABB, Rockwell,
Foxborough as well.
Foxborough. Yep,
Okay. Perfect.
yep.
Awesome. So for those of you out there, don't let just think that it's a Delta V application. We can actually implement it on many different platforms as well. Now, this is I usually have my own little slide here, but Devin put in his slide, and it's actually a lot prettier than mine. So let me see if I can actually do my pen here. So as we go up this way, we're going down that way. So the idea here is when I go in, and it's just universal for any kind of troubleshooting, and I encourage you to do this, is that the first thing that we must have is a properly designed process. Your piping, your tank sizes, your pump sizes, your cyclones, everything else must be properly designed in order to achieve good control. Afterwards, we got control philosophy, control strategy. How is it programmed within your DCS to make sure that you get good control? Instrumentation, critical. You got to have the right instruments. And I say, I'm a, feel like I'm setting my soapbox here, but specified, installed, and maintained. On the other side of the equation, your control valves must be properly sized, dynamic, and precise. If we do not do a good job with that, we will not be able to achieve any good PID control, let alone after that, it has to be properly tuned. I always say that loop tuning is the last thing you do. Not exactly true, because after that, you can implement state-based control and obviously, while we're here, advanced controls as well. State-based control, for those of you who don't know, is you kind of change your control philosophy based on what state your process is in. Could be in startup mode, could be warm-up mode, could be winter mode, summer mode, high high production mode. So therefore, your controls based on what state your process is in will change. You could change the tuning, you can change interlocks, you can change alarms as well, priority of alarm, suppress alarm, enable alarms based on what state your process is in. So it's something that actually is probably alongside advanced controls, state-based controls is probably one of the more underutilized control philosophies out there. And then after that, obviously, we talk about optimization on top of that. And then there's that magic word right there, where's my cursor right here? Sustainability as well is very, very important to be able to maintain what we have achieved. I know, Devin, do you have anything to add to this?
No, I think you covered it well.
Awesome, thank you. So like I said, we need to have a proper foundation. So obviously the first thing is the discovery part, the feed study to be able to establish where you are. We establish process related issues. We address instrumentation gaps. We talk about optimization of the PID loops before we even think about advanced controls. So actually, I'm going to start talking less and less now. So yay, all right. And Devin's going to start talking a bit more. We're going to deal here, as I talked about, the grinding circuit, flotation circuit, and the thickener circuit. So maybe Devin, you can talk a little bit more about what does the grinding circuit do. And I know here, well, I'll let you to talk to this slide right now.
Sure. Yeah, no, thanks, Sylvain. And yeah, obviously there are a lot more applications and processes throughout mineral processing facilities, and they'll vary depending on what your operation is. So, you know, a potash site definitely looks a lot different from a copper mine. But we've picked three of the big ones in, you know, typical hard rock mining processes. So your grinding circuit, which basically takes size feed from the crushers and breaks it down to smaller particles that can float in flotation. So the grinding circuit, you're really focusing on getting that throughput. It's often a bottleneck. It's also a huge power consumer, so you want to limit the amount that you use, and you need to make sure that particle sizes are properly crushed and sized for flotation. Flotation's all about recovery. So it's really about making sure that you're separating your product from the undesirable materials and getting into a purity that you can sell. But you're doing that in a way where you're recovering as much as possible. And then thickeners are typically on the back end, but they can also be middlings thickeners in the middle of the flotation process as well. But they're slower separation processes, typically where you're dewatering or you know, getting rid of or doing a little bit of dewatering before you're drying a product or a tailing slurry.
So that's what my understanding. The thickener may have a bit of a dual purpose. Is to recover some of the product, the concentrate, right, and that it gets processed later on. But also the thickener is there because obviously mining application, you have tailings, big ponds, and water is it's a big consideration from environmental point of view and so forth. And obviously
It is.
proper operation of a thickener helps reduce the amount of water in the tailing ponds, correct?
Yeah, absolutely. Yeah, the process is the same, but the application and the benefits vary depending on how you're using and where you're using it in the process.
Got it. Let's talk about some of the grinding circuits. So I'll just kind of
Right.
maybe I'll backtrack a little bit here and I'll let you talk.
Okay. So yeah, grinding. This is typical grinding setup in a hard rock mining facility where you've got crushed feed. So it's taken those super large particles from the mine itself and gotten them down to on the scale of inches. And then there's typically a SAG mill that feeds a ball mill within the entire grinding circuit. So it's getting particles from inches down to microns. So in the case of copper, they're targeting 100 micron feed to flotation roughly.
So it's almost like is that powdery form or sand form, or what texture would that have?
Yeah, enough that it can float on a bubble of air.
Got
basically.
it. Okay.
Yeah.
Interesting. Now, typically, does a grinding circuit go from a SAG mill to a ball mill, or is it a ball mill sometime? Go ahead.
Typically SAG mill to a ball mill. Okay. There's lots of different configurations. There's rod mills in there. You can have multiple ball mills in series or in parallel. But the big one that we'll see in hard rock mining anyways is a SAG mill feeding a ball mill circuit, like what you're seeing here.
Okay.
They're huge energy users. Again, especially the SAG mill will be the majority of energy use on site, definitely the biggest draw. It's also often the bottleneck because it's a huge, expensive piece of equipment. So very challenging to operate consistently and reliably. And for multiple reasons. A big one in mining that we'll see over and over again is that you don't have that precise measurement that you have in chemical processing or refining, where you know exactly what's coming in and exactly how much it is. In mining, you've got variable particle size, variable feed rates, variable composition, depending on where that ore is coming from and the location of the mine. And so you've got to deal with that uncertainty through controls. So that's a theme that's going to be pervasive throughout this talk today. What operations has to do on the SAG mill is they've got to figure out how do we coordinate the feed rate to the mill with the speed of the mill. They're usually on variable frequency drives, not always, but most of the time. How do we set how much recycle do we feed back into the front end of the mill to maintain that optimal load, and how much water do we add to get the right density within the mill?
Right.
So it's a challenging process, and again, it has a huge impact on overall mill operation.
So it's a very linear process. So everyone's got to work together. So you got the SAG mill down to the thickener, down to the flotation,
Right.
to the thickener. So everyone's got to work together, and you don't have a lot of buffer in between to kind of
not a lot of inventory, definitely.
To forgive any kind of changes in production rates, right?
Yeah, exactly. Yeah, you might have holding tanks with capacities of 5 minutes in there, maybe.
That's it. Yeah.
But that's about it. Yeah. So measurement's a challenge for sure, especially on the feed end. And there are starting to be more and more camera-based analytic sensors that might be able to get you particle size information, at least on the surface.
Okay.
But you do need a big part of this. A crucial part of this is measuring the load in the mill itself. So we've worked with based on bearing pressure, which will sort of give you the weight, but it's subject to drift based on how well maintained that bearing system is, the state of the liner, all sorts of other factors based on the state of equipment. I'd say best case scenario for a lot of these applications is if you've got technology like an acoustic array or a mill slicer that will show you exactly what the load is in the SAG mill itself, as well as where you're getting that impact point, which is a critical control variable.
Okay, cool. So you actually have acoustic that listen as to where as it's rotating, where is it actually falling on the other side?
That's right. Yeah.
Wow.
And there's a big difference in sound if you're impacting rock on liner versus rock on rock, versus if you're building up a large load and it's not falling as far.
Interesting. Okay. Very cool. Very cool. So what am I looking at here?
So this is a bit of a before. We got a nice before versus after shot here, but this is the before case. And so basically, operators they've got a pretty hard trip limit on the unit. So they've set an operator alarm, which you can see is the red line there, a little bit away from the trip unit, and the trip is based on maximum load of the mill.
Right.
So they want to make sure that they're not loading it up so much that the unit goes down and they lose a whole bunch of throughput. So you can see over the course of roughly a month is that operators, there's a ton of variability. And again, this is variability from feed quality, feed rate, composition, hardness. And so operators, they try to keep it safe and move it away from that trip limit.
Right.
What we've been able to do with control is, by coordinating the inputs and also by getting a bit of adaptive control in there. So when we see that variability start to increase, probably because we got harder, larger particles feeding the mill, we'll actually back off of that limit a little bit more. And then when we get that fine, nice, easy to grind particles, we'll push up against the limit. So we can say consistently within the level of tolerance, even under varying feed conditions. And so, this is awesome before versus after shot, showing an average increase in throughput of about 2.5%. What this isn't showing, though, is that they were actually able to take that limit, which was again set away from the real trip limit, because they had way more confidence in it. They were actually able to move that up and get a lot more than double the incremental benefits from running on control there. Yeah,
that's sort of your classic example of optimization, basically, right?
Yeah, reduce the variability and then shift it.
Exactly. Yep. You got it. Talk about the ball mill a little bit here.
Yeah, so this is the other half of the grinding circuit. So this is being fed, when it says from screen there, that's coming from the sag mill.
Okay.
So a big part of the ball mill, maintaining the load of the ball mills, is coordinating this huge recirculating load. So what comes out of the underflow of the cyclones goes to the ball mill and gets recirculated to that pump box, which gets pumped to the cyclones. Now, what you want to do is you want to keep that recirculating load at a nice steady level, so that the ball mill's doing work and grinding, and you're getting good particle size out of the top of your cyclones going to flotation. What you really need to make sure that you avoid is overloading the circuit, though, because that can quickly fill up the ball mill, which is a bit of a cascading situation there. And if that happens, they'll have to shut down the process. Hopefully they can catch it before operators have to dig it out, because that is definitely an undesirable situation. So it's really important not just to control the way that you're running your cyclones and your ball mill, but that's coordinated with sag mill operation. So if you see this start to get overloaded, you can actually dial back on the sag mill, and sacrifice a bit of temporary throughput, so that you don't run into a situation where you're overloading the circuit and down for a while.
Perfect. Talk a bit about flotation here. So how does flotation work?
Right. So flotation, again, we're moving downstream, like you said, linear sequential process. So the feed from flotation, at least the course of the rougher cells, is coming from that ball mill and the overflow cyclones usually. So flotation is all about applying a bit of a surfactant or reagents that bind to the desirable material and make it hydrophobic. So the reason that we want to do that is that hydrophobic material doesn't like being in water. So then we put it in the flotation cell. We pass air bubbles through the flotation cell, and again, it's a fine particle. So those hydrophobic particles, they want to get away from the water. They'll bind to the air and they'll float over the top of the cell.
Okay.
So it's an effective way to separate the things that you want from the things that you don't, as long as you can get the right reagents to bind to your desirable material.
Okay.
Now, yeah, so this graph, it's not a perfect process. You can't apply a surfactant that only binds to the desirable material, so that you get perfect separation. There's a bit of a trade-off. The more that you try to recover all of the desirable material, the more you've got to pull over the top. And as you pull more and more over the top, you're going to start to get a little bit of that undesirable material, the tailings. So, you want to maintain that minimum viable or minimum acceptable grade, so that you still get that separation, but try to maximize recovery while you're doing that.
Okay. Very cool. So the best thing you could do is get somebody who knows to tell you how the froth, tell you when the froth in the rougher cells looks the way it should. Then you take a good long look, and you try to keep it that way. So basically, looking at that statement there is just sort of, if it looks good, I got to look at it, and all right, looks good, or I think I should do this, and then next shift comes around. Well, no, I don't like it to look like this. I like it to look like that, and therefore you got a lot of subjectiveness involved. And I think that's what we're trying to do, is trying to make it more consistent, more deterministic, more measured. And this is what sort of measured operation is what we're trying to do here, right?
Exactly. That works if you've got very experienced people that know the process inside out, which you may have, but assuming that they're out looking at the flotation cells at all times and know exactly what to do in every situation to respond to it.
Okay.
So, I think we can do better with automation, and we've shown that we can do better, especially when you get those newer, greener operations crews in there that don't have the ability to do that well.
It kind of reminds me a bit. Those of you, well, if you ever saw me, you know that I like to eat and I like to cook, and it kind of reminds me when I make a chili. And if you like the chili that I made today, enjoy it, because it'll never make it the same way, because I just kind of wing it. But when I make bread, I do make my own bread as well. That's one thing where you have to be scientific. You have to measure by weight, all your elements, so many grams of flour, so many grams of water, so many grams of salt and sugar and so forth. If you don't do that, then your bread could be very good. But all too often, I made doorstops until I started measuring everything. So here again, so making bread, you have to be you have to measure, you have to be very specific. If you want to make chili, well, all right, you can go ahead. One thing I see here, Devin, is under constrained system. What does that mean? Under constrained system.
Yeah, and that's kind of one of the keys to control. So basically, there's, you're trying to control the pull rate or the amount of froth that you're getting over top. And
Okay.
the
So
reality is there's
overflowing.
lots of ways to do that. So if you
Okay.
want to increase the pull rate a little bit, you could add a little bit more reagent. You could increase the airflow so that more bubbles up. You could raise the level. So there's multiple ways to do that. And if you're looking for a small change, you can maybe pick one and bump airflow up a little bit, let's say, and that'll get you a little bit more. But if you're looking for larger changes or changes over a long period of time, that approach doesn't really work that well. Basically what ends up happening is you make a little bit of change. Let's say you bump up your airflow, you start to get a little bit more over top. But then if you continue to do that, continue to raise the airflow to try to get more over top, you start almost boiling, or it's not actually boiling, but making the
Right.
float cell very, very volatile, and that starts pushing over that undesirable material, and you lose that separation effectiveness. You start getting tailings over the top. And so basically, what this boils down to is that our philosophy for control of flotation cells is don't just use one of these handles. Let's coordinate them and move them all together. So if we want a little bit more concentrate, we'll add a little bit of reagent, add a little bit of airflow, bring the level up.
Okay.
And this way, we get a consistent, reliable performance out of the flotation cell.
Okay. So it means that there's multiple ways to fix a problem. You can do it a little bit of this, a little bit of that, and so
Exactly.
okay, all right. That reminds me. So if you think about it, reminds me of like today. Apparently it's going to be a hot day on planet Earth in Mississauga. So if you have your air conditioning, I don't have fancy controls on my truck. I just have a air control. So you can have your AC on maximum and a little bit of fan, or you can have less AC, more fan. There's different ways of controlling the temperature just by adjusting the two knobs of the fan speed and the intensity of the air conditioner. So, and I guess that's what under constraint means. There's multiple solutions, and I guess this tries to accommodate all that. I see there's something called the block there says IQC. It doesn't say MPC. What's IQC?
So it's integrated quadratic control, and again, the handout is available for a lot more details on this. But it's basically our delta V based solution, or our solution to doing under constraint control.
Okay.
So it uses quadratic, to keep it short, it uses quadratic optimization, basically to coordinate things and move them together while trying to control block. We've got books online files for it. We tried to make it so that it's tuned using similar parameters to a PID block.
Okay.
So relatively easy to understand and get into. It's got a gain, reset, and a rate. Now it's a little bit more complicated because it's got one of those for each manipulator variable.
Okay.
But it's an effective tool for these types of under constrained applications.
And that's a block specifically developed under Spartan Pro Solutions, right? It's not part of the standard Delta V offering. You have to get this separately, I guess.
That's correct. Yeah.
Okay.
And with that, we've tried to include all the standard documentation and books online files and all that stuff you'd expect from any other Delta V block. But yeah, we developed that one.
Okay. Now I see that you could do that for one cell, but then you can also do this. There's a faceplate of how it looks, I guess.
Yeah.
Right?
Just want to mention here, one of the keys here too is that we get operators and metallurgists to interact with this control strategy. So they'll actually set the upper and lower limits. And the reason that this is so valuable and has led to high adoption of the solution is that the feed conditions change for flotation all the time. And again, we don't have the measurement technology almost always to detect those incoming changes to composition, to particle size, hardness, even coming out of the grinding circuit. So, the reagent amount that you use one day can be totally different from the reagent amount that you have to dose another day, just based on where you're digging in the mine or
Right.
where you're getting feed from. So, until we get AI to be able to tell us exactly where that is,
Don't get me
um,
started.
yeah, it's a little bit difficult to come up with consistent control that always does the right thing. So by giving operators and metallurgists these high and low limits, they can guide the process or set boundaries from the process based on where it is. But they don't have to babysit it to make sure that we're constantly pulling over a decent amount of feed or concentrate from our flotation cells.
Okay, interesting. And then we can actually from one cell, we can actually work on bank cells and then multiple banks after that.
Yeah. So, the quick version, I know we're running out of time here, but we don't want to pull the same rate from every single cell. You get higher recovery off of your first cell and significantly less off the back cell, almost always. So, if you need to drop pull rate because there's a change in flow, it's kind of better to leave those first cells high so you maintain that high recovery and drop the flow off the last ones, and then slowly stabilize. So we can achieve stable control without significantly upsetting or having a huge disturbance to recovery.
And most of the recovery, correct me if I'm wrong, is usually done at the front end, correct? And the rest is just kind of picking up the crumbs after that.
It is, yeah. So depends on the process, but it definitely decreases over the number of cells in series.
Perfect. Okay.
So this strategy, basically the way we've set it up, is IQC will cascade to the local individual cell controller, which again adjusts things like airflow, brine addition, water addition, cell level, reagent addition for those individual cells. So we've got a local controller maintaining stability within the cell, and then a overall controller coordinating the different cells.
Okay. So it goes more further up in sort of a hierarchy, I guess.
Exactly, and it doesn't stop there. If you go to the next one, I believe. So then we won't just stop at an individual bank. We can actually look at the circuit as a whole. And with the circuit as a whole, we can coordinate, what's going on the roughers or coarse flotation versus the scavengers versus the cleaners and tailings. And if we're a little bit low on product grade, we can, decide to back off a little bit, and we can do that selectively, like maybe back off on the scavengers before we back off on the roughers.
Okay.
Or if grade is high and we want a little bit more net recovery, we can also pull a little bit harder across the entire circuit. So it really helps drive that value. And we had that pull rate versus recovery trade-off curve that we're really trying to optimize with that top layer.
Awesome. Okay.
Yeah. And I believe if you
I think we
keep clicking there.
Okay.
Yeah, sorry. I guess I spoke ahead of this one.
No, that's all right.
Yeah,
No, it happens to me.
It really is about coordinating the entire flotation circuit across site to maximize that trade-off between grade and recovery.
Awesome. And then that's where the money is, actually, to be able to maximize.
Yeah, stability's nice, but this is really where the money is for sure.
Exactly that.
Mm-hmm. So when you zoom out, this is what the control strategy looks like as a whole. We're trying to control product grade, but then we've got decentralized control. So we've got separate control for the roughers and separate control for every cell within the rougher.
And all this has to be kind of looked at by the metallurgist in conjunction with the lab and the operation as well. So they'll make these adjustments on a daily basis, on a weekly basis. I guess it depends on the type of, like you say, on the grade of the ore that they're pulling out.
Yeah, some mines are nice and consistent and have steady supplies of high consistency ore. You're probably jealous of those mines because most of them vary from day to day or week to week, and you got to make adjustments. Metallurgists have to make adjustments based on that.
Interesting.
So we're trying to take a best of both approaches where, we're putting the power in the hands, and we are still, relying on some input from operations and metallurgists, but they're really there to guide the process and manage the process rather than having to micromanage it with every small feed rate change or minor upset that you
Right.
get.
Okay. Let's talk about, there's, we've got more about flotation. Yeah, go ahead.
Yeah. So, it drives a lot of value, and a lot of times this is tough to measure directly because you're not measuring recovery rate or grade off of each one of those individual cells or banks. You're just kind of measuring final tails and final product. And lots of things change day to day in the site. But we've done a bunch of these projects. All of them are around the same value where, there has been an increase in grade. We're not entirely sure how much to assign fairly to flotation advanced controls, but it typically falls between 0.5% and 1% increased net recovery, which if you're a mine that's already running 89, 90% recovery, that's huge.
Right.
And it can have significant value.
People don't think that just a 1%, 0.5%, 2%. I mean, those are big numbers. It's the gravy. It basically is the gravy on top of your French fries.
Yeah, and there's also no increased operating cost or very minimal increased operating cost for that because
yeah.
you're not increasing the amount of ore that you're processing or mining from your facility. You're just getting more out of it.
Exactly. Awesome. Let's talk about
So,
thickeners.
yeah, thickeners. Last but not least, it's a simpler control problem, and again, there's lots of different applications for thickeners. So you've got middling thickeners, where it does impact product recovery. It's a big, slow separation process that may be somewhere between the roughers and the scavengers to improve removal of the tailings and better separate your product. Or it can be final tailings thickeners, where you're trying to remove the water, reclaim the water, and minimize the rate that you're filling up your tailings pond at. So lots of different use cases here. But what they have in common is that they're these large, really, really large, high residence time settling tanks.
Okay.
And what they really do is they allow the solids product to settle to the bottom, and then it gets removed out of the bottom. And then over the top comes the clarified or hopefully clarified water or brine or whichever it is. So the real challenge here is that it's slow. And this is why model predictive control is an effective control strategy, right? It's really tough for human operators, you, me, to react to changes that took place because of something that happened 3 or 4 hours ago. Like our brains just don't work that way, especially over things like coffee breaks and shift changes. So when you get to thickener operation, there's a tendency to run safely. And safely in thickeners usually means pulling thinner underflow than you normally need. So you're just pulling more out of the bottom, and you're not doing it as effective job of really separating the process.
Right. Interesting.
So
Okay.
oftentimes there's a lot of value. If you can do a better job of predicting what's going to happen, you can increase that underflow density or underflow solids to a kind of a maximum level that your underflow line or underflow pumps can handle. Then you can do a better job of separating. You can also watch, some applications require that you watch the turbidity of the overflow. So all sorts of constraints you can incorporate there. But MPC does a great job of this, again, because not because it's an overly complex application, but just because that long gradual dead time.
Got it. Yeah, we're all, let's face it, we're all impatient, right?
Yeah, absolutely. So again, results are going to vary. In a tailings application, we can do significant reductions in the amount of water loss that you get while still doing an effective job of separating your tailings, which can have a huge impact, not day to day, but over the lifespan of a mine. It can be massive.
Right.
Other applications where you're trying to increase, where you're actually recovering product, thickener operation, despite the simplicity of the application, if you go to the next one there, so it can have huge value. And again, being able to increase product recovery just by getting higher solids out of the bottom, that can have massive value for operations,
Awesome.
which matches or exceeds some of the other applications throughout the process.
Right. Yeah. No. Exactly. It's now we do have some other applications as well that are available. We're not going to deal with these right now. I know we're getting time at the end. We're probably going to run over a little bit, so please bear with us. We will be answering questions very shortly. So we do have other applications as well that, as you can see. If you have any interest in any of these, feel free to reach out to me, and we'll make sure that your inquiry gets answered. Now, okay, so we want to implement this. What sort of timeline are we looking at here?
Yeah, so it varies, but we want to follow a process that leads to that sustainable operation and realization of the benefits. So for a typical application, it will, we'll start off with a proper front-end engineering design phase, make sure that control foundation is in good shape, and make sure that we have the functional requirements and all these operating scenarios that we need to handle and well developed. Then we'll go to configuration, testing, and then finally tuning and commissioning. So that whole process takes roughly 4 months, start to finish. Of course, if you're, it's a little bit different if you're doing one thickener versus if you're doing the entire flotation circuit. So there's, a little bit of flexibility there.
And it all depends also even where the instrumentation gaps are. You need to buy new instrumentation, do this, do that, or even some process modification. I mean, let's face it, that's going to take a while too. So that's sort of the big unknown as to in the front end engineering will determine that, and that's where that uncertainty of time based on what's required to get the maximum out of your APC.
Mm-hmm.
And obviously, yeah, so we got some hardware. If it's a non-Delta V system as well, some hardware and software that needs to be implemented as well. So okay, so now we got it running. Okay, we're all happy, and then suddenly, what happens most of the time, very, very often, I should say, or is the fact that it gets turned on, it works, and then suddenly it gets a little bit used, a little bit less, a little bit less, a little bit less, and it kind of dies a slow death typically.
Mm-hmm.
And this is where the difference here is, where what we are offering, what we actually strive for, is to make sure that it is, what's that word again? Sustained, meaning that we're able to maintain that system, and that requires a constant monitoring of the process, of the controls at different levels, at different timelines, to make sure that we're getting the maximum out of our controls. And I'll let you speak to this a bit more.
Yeah, I mean, I think this speaks to the value that Emerson, I mean, I'm biased, but the Emerson Impact Partner Network, where we are local, we're not going anywhere. Our customers aren't going anywhere. We want our customers to be our customers for life. So as part of that, we need to make sure these applications aren't just, don't have a 3-month or 6-month lifespan. So the sustainability is important, and it has been from day one for us. The effort doesn't need to be massive, but it does need to be planned and intentional. So, on a week-to-week basis, we just want to watch KPIs. Something as simple as our operators using it is often a good early warning indicator.
Exactly.
If it's not working or if it's doing stupid things, they'll stop using it.
Yeah.
And the faster you can get on that stuff and correct situations that are occurring, the better. And it might be a faulty transmitter, or it might be that the controls don't handle a specific scenario as well as they should.
Exactly.
Yeah.
Now, one of the things also is a lot of this stuff can be done remotely as well. So you don't have to have a person go to site on a periodic basis or continuously. This can be done remotely as well. So it can be done very cost effectively.
Mm-hmm.
So where do we begin? So there's a 1 to 4 day investigation here. Obviously, we kind of talked about this. Go ahead.
Yeah, I was going to say, some customers know exactly what process they want to start at. The grinding circuit's a huge problem. Let's start there. Others aren't so sure what makes the most sense for advanced process control. So one thing that we can do is come in and do one of these advanced control opportunity assessments, and basically determine what makes the most sense. Which area are you going to get the most payback for, has the lowest risk, are you set up for most effectively on the instrumentation and actuation and regulatory control end. So we can help make that investment decision easier.
Awesome.
And we'll try to deliver it in a clear and concise method that, evaluates effort versus payback. Might flag some applications as it doesn't make sense under the current economic situations versus other stuff is, this is a quick win or a no-brainer. And those are really the ones that we're looking for.
Awesome. Oh, that's great. That's great. So here we are at the end here. So that picture you're seeing right there is my colleague Chris Folds at a mine, and maybe we're not allowed to barely show that, but we are. He's holding a gold brick there, probably worth I think it's worth in the millions of dollars, and this is where this is what it's all about. It's about being able to maximize the profits, whatever we're mining: gold, copper, silver, zinc, nickel, whatever you want to watch. What do you want to say? So we're opening it up for questions right now. And Devin, we do have a question here. So question one, are all your APC controls are based on 𝗪𝗕𝗦 control systems? I'll let you answer that one.
Yeah. So our mining applications so far have all been in 𝗪𝗕𝗦. Now, I will add, it adds a little bit of a twist to this, but Emerson recently acquired a majority stake in AspenTech technology, which is a global advanced process control suite, mostly focusing on model predictive control. So they don't have things like IQC, but we can also have that conversation as well.
Right, exactly. Question number two, how do you coordinate basic process controls such as PID with APC controls for smooth operation? How do you switch between optimizing mode and normal operation mode? I don't know, do you get that question?
Yeah.
Okay.
Yeah. No, and that's a really important part of doing the advanced process control. And one, again, I'm biased, but one of the real advantages of doing it in 𝗪𝗕𝗦 is that, the configuration can take place in the same module even. So you can just like you might be able to cascade, a PID loop to your AO block. You can cascade an MPC controller or an IQC controller to your PID block to your AO block. So from the configuration perspective, it's simple and straightforward and all maintained in one system.
Okay.
In terms of switching between one between the other, again, the status propagation and other features like that within 𝗪𝗕𝗦 make that easy. But we'll also set up little procedure automation type programming features that facilitate that switching between modes so that you get that bumpless transfer, we get set point tracking, and all of that stuff. And
right.
We can, depending on the scenario and depending on the operation, we can set it up so that if operations wants to run the flotation controls, but they want to take cell 5 out and run it manually for a bit, with the rest of the cells still in control, we can make that happen, no problem. And it'll just use cell 5 as a feed forward signal.
Awesome.
So,
okay. Very cool.
Long
very cool.
answers there, but I hope that covers it, Bill.
No, I think basically, the idea is that can you always go backwards? Says if it doesn't work,
Yes.
can you go backwards? And I think that's sort of that's always switching to manual, Captain. As they do in Star Trek, because for some reason they're still putting stuff in manual in 23rd century, but towards the 24th century, I don't know. All right, just so we're going to pause here. We're still have a few minutes here, and if we'll just see if there's any other questions throughout this as well. And so now we can maybe play a bit of music at the same time as we wait. I'll turn it down a little bit. So we'll see if there's any more questions. It's always that awkward part. That music, by the way, Yeah, the music, by the way, is from the Good, the Bad, and the Ugly. If not even any of you ever heard of the Good, the Bad, and the Ugly movie, it's one of my favorite movies. So it's right at the end, the very last scene where they discovered the gold. So we'll just let it go here for another few minutes, see if there's any more questions. As I said, always reach out to me if you think, geez, I should have asked this question, I should have asked that question. Again, feel free to reach out to me and we'll make sure that it's answered properly. And I'll turn it down a little bit, tad more. And like we got to take into account the 10-second time delay too.
Mm-hmm.
Well, we'll pause a little bit longer here. So hopefully you found this informative. Like I said, we got many mining application opportunities in Ontario and in Manitoba. So hopefully, I know some of you are involved directly with mines. Some of you are working for consultants. Hopefully, to be able to leverage off of this, and we'll be able to see you in the near future. I know from the last time, this is our second webinar, by the way. I know we actually did one back in, when was it, Devin? Was it April, was it?
I want to say April. Yeah.
Yeah, I want to say April as well. Yeah, definitely. And so this is great. We're trying to catch, obviously, the off shifts. If you go to mining sites, 2 weeks on, 2 weeks off. So this is why we had a second one happening here. It looks like it's pretty quiet, Devin. It doesn't look like we have any more questions at this point. We'll just give maybe another 15 seconds. How about that? 15 seconds.
Sounds good. Our time or their time?
Yeah. Probably our time.
Well,
no, maybe another.
Thank you for having me.
Yeah, it's been great. Obviously, Devin, thank you very much. It's been great. And certainly looking forward to doing some more of this collaborations as we go along. We progress, be able to maybe do a case study or something like that. That'll be the next step after this. Be able to do that would be fantastic.
Absolutely.
All right. Well, it looks like it's pretty quiet. I want to thank everyone, specifically, obviously, Devin. Thank you very much for attending. Appreciate it. And thank you very much for attending. And like I said, please feel free to reach out. I know some of you have already started reaching out to me already. Appreciate it. And everyone have a good day, good safe day. And obviously we'll try to make it back from our spacecraft as safely. So thank you very much. And we shall see you in a bit. Thank you. Take care. Thanks, Devin.
Thanks, everyone.
Take care.